All right, welcome. This is part 2 of our discussion of the DragGAN paper. So we watched a video last week covering the basics of the paper. I'm going to do a recap of what the model does, and then we'll watch some of the second half of the video where he actually talks about his implementation to get a sense for the code. It's kind of interesting. It's not really that long, the code. And then I do have a copy of his code, but instead of that, since then, the authors of the paper have actually released their code, and so then we can play with the actual model a little bit. All right, so let me share my screen. And are you
What
guys
is
seeing
that?
like the Colab?
No, we're seeing some cool little red sort of thing.
I'm sharing the wrong screen.
Oh,
Sorry. I knew it didn't look right. There we go. All right, I got a bunch of windows open. So first thing I'm going to do is I'm going to open up chat and share with you the notes for this paper.
oh, thank you for expanding it.
All right. So here are the notes. So quick recap on this.
Ted, we don't have access to it.
Really?
At least that's what's telling me.
I thought this folder was. Already. All right, you guys should be good now. All right. So this is the template that I've used before. So here's information on the paper, their blog, and their GitHub repo with the code. Okay. The key papers that you might want background for this paper is this is the original paper on GANs, and then StyleGAN 1 and StyleGAN 2 papers, since this paper is built on top of StyleGAN. All right. Quick, I'm gonna go through the notes, but before I do that, just super quick, like what this paper is about is that we can take an image from the GAN, we pick points, and we say where we want them to move. So red is the original point, blue is where they want it to move to, and then they run this model, and it'll change the generated image the way you asked. So I don't know why this video's. There we go. It looks like it's playing again. So each time they do a set of red and blue points, it's them. All right, let's try it. Well, so, okay, let's just use the still images. So in this case, they said on the right here, we're gonna have the cat's right eye, I guess, on the left from our perspective. We're gonna move the top and the bottom together to close the eye, but we don't want to close both eyes. We're gonna tell it specifically to keep these points the same, and so then they can have a picture of a cat that's like winking at you. All right. And this lion, what do? They open the mouth, and because it's in the space of realistic images, it's not a big black empty space when it opens the mouth. It says, oh, there should be like teeth and a tongue and everything, once you do that. And then in the second edit, they said, okay, let's turn the head a little bit this way. So now the lion, instead of looking straight at you, is looking off to the side. They changed the length of I can't even tell if this is pants or skirt legs or whatever, but we'll change the length of the clothes. We can change the position of the feet, that kind of stuff. So that's the general gist here is much more specific, fine editing as opposed to just generally like add a table or something like that. No, it's like move this particular point this far on this image. So that's the cool thing that they're talking about in this paper. All right. And so again, in the video that we covered last week, right? GANs, you've got two parts. You've got the generator, the discriminator. Generator creates images, and the discriminator's trying to guess whether something's from the training set, what we call real images, or something that came from the generator, what we call fake images. And you sort of alternate. So you train the generator for a while till it can make pretty good ones, and then you train the discriminator for a while until it can figure out the difference. And then you train the generator some more, so it makes even more high quality images, and then back and forth. So there are some tricks to training, doesn't always work out well. And then one of the things I put in the notes is that if you look at this diagram, the only time that a signal gets back propagated to the generator is when the discriminator figures out that its image was fake. Okay, the real images never send a back propagated signal to the generator. So neither directly nor indirectly does the generator ever see any of your training images. So it's actually kind of amazing that this thing works when it never, ever, ever gets a signal from the training set. Now, where it does get the signal is that the discriminator in its weights learns about reality from the training set. And so thereby, even more indirectly, it is able to give a signal back to the generator. Okay, but that's one of the things that, you know, when I was studying GANs that I remember, I don't remember where I read that, but I was like particularly blown away that, wow, the generator never sees an image, and yet just by getting this back propagation signal, it eventually gets pushed in the direction of forming pretty amazing realistic images.
Ted, quick question.
Yeah.
You said the training cycle or regime is that it trains for a while until it gets it right, and then it starts training the generator, then training the discriminator. Is that kind of threshold driven, or does it bounce back and forth?
I'm not actually sure exactly how people do it, okay? But I've seen some things that say that basically you can err on the side of not training the generator enough. Okay. So if you don't train the generator enough, then basically the discriminator just gets really smart. It's like, it's real, that's fake. Okay. And the generator just needs to catch up the next time you train it. Okay. If, however, you don't train the discriminator enough, it can easily then fall into a regime where it stops learning.
Okay.
So it's more important. So I've seen stuff that just has some heuristics that says like the learning rate on your generator should be less than the learning rate on your discriminator in order to put it at a disadvantage, you know. Because the generator doesn't learn, then basically the discriminator may not get any better the next time you train it.
Right.
But if the generator just keeps getting better and better, then you could get screwed where the discriminator just gets lost.
Yeah. I guess the mental model I had is it's training, it's kind of going back and forth, kind of a cycle count thing, not a train for a while.
Yeah, and I'm not sure, people may actually do that where, like, you know, you alternate like one, you know, batch at a time as opposed to 1,000 batches at a time. I haven't done a lot personally, but either way, the idea is the same, is that you need the generator to be getting better to force the discriminator into getting smarter to tell the difference between real and fake. So in the beginning, it should be super easy for the discriminator to tell, because the generator is going to be kind of like static.
Yeah.
And then these are going to be like nice, pretty pictures.
Yeah.
So
yeah, I could see an algorithm that kind of said, let's keep them balanced. I want 50-50 would be optimal. I just hadn't heard that before.
So you could actually monitor the discriminator to see how well it's doing, and when and so on. Okay. And there's some details. I'm not obviously going to all the details, but that's the general gist. So style GAN came out, and the idea here is they wanted like discrete controls so that like I could have a user interface, and this knob would let me change the color of their eyes, and this knob would let me change the hair color, and this knob would let me change the glasses, you know, and so on and so forth. So how do you sort of disentangle all of those things to get them to be identifiable, separate, inputs, right? So the general gist is there's two big things they do different. So you start with a random number generator, and maybe you generate 512 floating point numbers. They run it through a very large, just regular old dense, fully connected neural network, which changes this from a uniform distribution to some other, could be any possible distribution. And then the real magic happens in this architecture where they start with something very coarse. It's just 4 by 4 in terms of the height and width. Okay, but in terms of channels, it's actually very deep. So it's a little bit like, when you have an autoencoder or whatever, right? The decoder side, starts out small in the height and width direction, but deep in channels. And then eventually, as you keep upscaling, then you lower the number of channels, and the final output is going to be 3 channels: red, green, blue. So you start very small, 4 by 4, and then after you do a couple of operations, then you upsample it, so it's 8 by 8. And you do a couple of operations, upsample it, 16 by 16, and so on and so forth. And so this adaptive, what the heck is that again? I'm trying to remember. Adaptive instance normalization. Basically what it does is you've got this little module here, which is usually just like a single layer network that kind of chooses what subspace of your latent to utilize. And based on that, it then it normalizes the input. So I think it's like whatever, I don't remember, 0 mean, 1 variance or something like that. And it applies a multiplicative constant and an additive constant. Okay, so the output of this little A box is what do you multiply by and what do you add? And I was thinking about this a little bit, and I think the add is more important than the multiply. Okay, so basically adding a number lets you just sort of, change the values in this feature map. Okay, and it does it every single layer. It does this over and over and over and over again. And when you train long enough on this, what ends up happening is that these inputs up here early on end up changing very coarse things. So like if you're doing faces, it might do like the overall shape of the head, the overall shape of the hairstyle. I'm not sure, but I would think that like your overall skin tone, right? And then like a little bit later, you'll get things like, do they have glasses, and maybe like their eyebrows or something. And then way in the very late stages will just be very fine details about like, okay, on this side of your cheek, is it shiny or is it not shiny? Or is it a little bit redder or what, like you just get those super details. And so if you have a particular hairstyle, that'll get set maybe in the middle somewhere, but the actual individual hairs, over here in this section and how they look. So what color and all that will get decided early, but like whether these particular hairs maybe are sticking out a little bit more or laying flat a little bit more or whatever, do you have a widow's peak? Like that kind of stuff is going to happen relatively late. And that's the overall gist of StyleGAN. So any questions about that? All right. So then what they do in this paper is
Ted,
they go to, yes,
Ted,
Jerry.
one minor thing. We're seeing your little Windows update box.
Oh, sorry.
Thanks.
So what they do in this paper is they experimented where to look, and they looked in the 6th layer. They said, oh, the 6th layer is a pretty good point where like we can change some big general things. Like if it's a picture of a dog, you can change the pose. Is it sitting? Is it standing? Is it looking directly at you? Is it looking to the left? Things like that. And the key concept that they believe to be true, and I would say have proved to be true because their model works, is that let's say your full image is 1024 by 1024, but the sixth layer that they're dealing with is, let's say it's only 256 by 256 in its height and width. Okay, so it's 4 times smaller. They end up upsampling it, so it's also the same resolution, 1024 by 1024. But the key thing that they're looking at is there's 2 properties. One is that the upper left corner of that feature map directly correlates to what the upper left corner of the image is going to look like. And the same can be said for the top middle, for the upper right corner, for it basically, like, you know, position wise, X, Y coordinate wise, everything in the feature map is predicting what that portion of the eventual image is going to look like, that there's direct correspondence between the position. So if I look at the feature map in one spot, and let's say eventually that becomes, you know, the person's nose, okay, then the spot directly above it will correspond to the spot on their face that's directly above their nose. And the spot to the left of that will directly correspond to the part of their eye that's directly to the left of that, and so on and so forth. That there's no deformation, there's no, you know what I mean? Like, it's just, no, literally, if you go a third of the way to the left, that corresponds to the pixels in your image that will be a third of the way to the left down the road. So that's key concept number 1, that this DragGAN architecture, all the feature maps, those features are physically located in the exact corresponding place where the pixels eventually will be. The second principle that they had was that those feature maps are not sort of vague general things, but that they're actually very detailed and corresponding to what is eventually going to get generated. So if you look at the feature map for a set of pixels that's going to eventually be the nose, that they will have different values than the feature maps of something that's eventually going to be the ear or eventually the forehead. Okay. Now they did find like a counterexample that if you had something like a car door and it was just sort of like a uniform, I think in the paper it was red. So it's a red car and there's this region of it where everything just looks kind of the same, right? There's no special texture, there's no whatever, it's just all red. Then they found, in fact, that all the different feature maps for that region were pretty similar and it was very hard to tell them apart. Okay, because the eventual pixels were almost all the same and it was very hard to tell them apart. So when you have a very uniform, smooth section of the picture, this may not be that helpful because everything is uniform. But any place where you have variety in the actual picture, the mouth will look different than the nose, will look different than the eyes, will look different than the hair, look different than whatever. So those are the 2 principles they use. Yeah.
Quick question with this picture up. The noise coming in from the right-hand side, I assume that's projected into the entire latent space, but not latent, the entire hidden layer, what I guess you would call it. In other words,
yeah, so if you allow this random number seed to float, then even with the same random numbers coming in here, you can get slight variations in the image. So you could fix this Z, and that could be, let's say, whatever, a picture of a poodle, you know, sitting and whatever, you know.
right.
But you could get ever so slight differences in terms of the way the hair looks, the you know, the head could be tilted a tiny bit, little more, a little less.
So
if you fix all of these, then of course you'll just get the exact same image pixel for pixel every time.
So in this work, do they hold the noise constant, do you know?
I don't know, but I would assume yes.
Okay.
Because what they're trying to say is you like the image you got, you just want to change one thing about it. So if you do this, then it'll change more than just that one thing. It'll also just have slight differences.
Yeah.
Is that noise additional noise on each cycle, or is it just one? Is it just come out just once? Maybe I'm not phrasing that right, but
In the original style GAN, when you're generating one image, okay,
Hmm.
the data only goes through once. So you do this latent,
Right, right.
and it creates all these A's, and then you start here at the top and you just work your way down until you get from 4x4 to your final resolution. So it's just one pass through. It's taller than you can really conveniently
Yeah,
show on a piece
yeah.
of paper. This very tall stack of these
Mhm.
layers. Okay, so it's kind of like I don't even know how to explain it, but basically this latent really controls what you're going to see, and this noise controls the fine details where, again, at the coarse level, the noise is going to be, the head pose might be ever so slightly different. You know, in the middle layer, maybe it's like, do you have a mole or not a mole, or maybe just the size
Mhm.
of it, you know? And then
Mhm.
at the very lowest layers, like I remember in the original style GAN paper, you can see they zoom in on like one little part of, because I think they were doing celebrity faces in the first paper,
Yeah, I remember
one
that
little
one.
part of their hairline, and you'll see that it's like 5 hairs pointing like this. And when they change the noise, like 2 of them are slightly different. The hairstyle's the same, the hair color's the same, but like every individual hair is not identical when you let this noise change.
Okay,
But
thanks.
if you fix that, then it's like bam, it's completely, exactly the same.
Okay.
All right. And so once you have those two principles, that the feature maps correspond exactly to the corresponding locations in the eventual image, and that, in the author's words, that it's very discriminative, that you can tell the difference, then you can do two things. Okay, you can basically say, so I have this feature map and it has values 1, 2, 3, 4, 5, 6, and it's the nose. So if I want the nose to be over here, what I need to change the feature map over here to be 1, 2, 3, 4, 5, 6. And that's essentially what they do in the first step in the motion supervision. So they basically just sort of calculate a loss between what is the current feature map over there and 1, 2, 3, 4, 5, 6. And so then they figure out, how would I tweak my W, my latent, in order to get this thing to be as close to 1, 2, 3, 4, 5, 6 as possible. And the second thing is, they said, okay, if you're doing a big move, so let's say I'm going to turn my head to the side, all right? So now it's going to move from there to here. Once I've moved part way, you're no longer trying to get this to move over here. You're trying to get this to move over here. Okay? So you have to actually, so you have your handle point, that's the starting point, and you have your target location. You have to actually keep updating your handle point as you successfully move it. Otherwise, in the example of this, if I'm turning, now I'm going to be moving this cheek in that direction instead of continuing to move my nose in that direction. So the point tracking, they did something brute simple again, where they just said, oh, this XY coordinate over here, like 100, 200, used to have the values 1, 2, 3, 5, 6. Now we did an update and it moved a little bit. Let's find which feature map in this general area is the closest to 1, 2, 3, 5, 6. And if we think it's this one, then we're just going to update our handle point to be where that one is. That's the super nutshell version, recapping what we saw in the video yesterday and how this model works. Any other questions about that? All right. So then I'm going to go back to the video we were watching last week, and I'm going to continue playing from here. And you guys let me know how much you want. Like, we can watch the whole thing where he's walking through the code, but basically what he's going to walk through is the steps that I talked about. So they're going to pick a random number seed, and that's going to generate their latent vector W. And at some point, you're going to go and you're going to get the 6th layer. It's going to be, right, a square feature map. And they're going to do 2 steps. They're 2 processes. They're going to do the motion supervision, where they try and get, the feature map, in the desired direction to look more like the one where you started. and then they're going to see if they need to update their handle point. And they're going to repeat those 2 steps. Typically in the paper, it says 30 to 200 times. All right, here we go. Somebody shout if we have any problems with the audio or the video.
I would say the whole magic behind the paper, and now let's just implement it ourselves. So this is the official repository for the DragGAN paper, and the code will be released, I think somewhere was stated, yeah, code will be released in June. But I found a different implementation, and I just tried to pick the essential pieces of code, put them together in a Colab notebook, so we can basically go through and understand how we can code the Drag Your GAN paper ourselves. And that's what we're doing now. So we go through this. First, I would like to give credit, one, to the authors of the Drag Your GAN paper, of course, also to the authors of the DragGAN model. Also, the DragGAN was only implemented in TensorFlow, so there is a PyTorch implementation. So also thanks to Kim Seong-yeon. That's halfway pronounced correctly. And last but not least, also to the author of the Drag Your GAN implementation that you can find here. And yeah, what do we need to do to re-implement the Drag Your GAN paper? First, I basically broke it down into a pseudo code. First, we need to generate our latent code Z. Then we need to map the Z to an intermediate latent code W. What we then need to do is to generate the feature maps of the 6th layer of this DragGAN 2 generator. Then of course we need to define our handle and target points via drag and drop. Yeah, this point I skipped in this tutorial. We will just do it manually, but yeah, ideally for better editing you would do drag and drop. And then, as the whole magic of the Drag Your GAN paper, we will iteratively optimize our latent code W with motion supervision and point tracking. And at the end, of course, I will show you the edited images, and we will see how this whole approach works. And I will also show you the limitations, because the demos look really, really cool, but there are also some limitations that we definitely should be aware of. So don't miss out on them.
Oh, by the way, the link to this Colab notebook is in the notes. If you scroll down, the video and his Medium article and this Colab. So if you want, you can actually follow along his code. I have that code. I tested it. It runs. It works. It's slower. It does work. I'm going to be showing you the official implementation.
Okay, and first what we're going to do is to install the DragGAN 2 model, or as we saw here, the PyTorch implementation of DragGAN 2 by cloning the repository and installing required modules. So I'll just execute and run this one. And in the meantime, yeah, I did a small customization of the DragGAN 2 generator, just because in this in the implementation here, in the forward process, we each time calculate the transformation of our input vector Z to our intermediate latent W. And yeah, we actually just need to do that once. So I split this into 2 pieces. That's actually the only thing what we're doing. So we are still importing that generator and just having one method that prepares our intermediate latent W, and the other one is just for the image generation process and also getting our feature maps inside the generator, so that we then use for our motion supervision and point tracking. Yeah, so this is basically our customized DragGAN 2 generator, and with this we can easily do the first 3 steps. So we can generate our latent code or initialize it by just having a random vector with a length 512, which basically is a 512 dimensional input vector. And then we map this input vector to the intermediate latent code W. And for this, yeah, we initialize our DragGAN 2 generator and then call the prepare function with our latent code Z. And what we will get back is our latent code W and noise, which, for example, if you have hairs or like freckles, they will not always be placed at the same position, or hairs will be a little bit more curly. So the noise is actually just responsible for adding a little bit of stochasticity. Oh my god, what a hard word. And what we will then do is to define our handle and target points. I would say I exclude the via drag and drop, as you will see here. So what we do is we manually define them. We have 2 handle points and 2 target points. Yeah, this is just a method or a util method to convert our tensor to an image so we can visualize our image, and this helps us to add the points that we selected to our image, and then we can see here how our initial image looks like. And here are handle points. Those are the blue ones are our target points. Here you can see, okay, this could be a little bit improved. I think this is pretty accurate already. One thing to know about the data set or the generator, the positions of the eyes, I think, maybe also the mouth and the nose, are standardized in the data set. So if you generate images often, they will be like in portrait mode, basically like this person right now. I'm like, it's not a real person, just to point that out as well. And yeah, so what I will do, I will slightly move them a little bit to the left. So maybe just do 405 and see how that looks like. Yeah, and I think this a little bit better. Maybe I could do it even a little bit more, but I think that's fine. And what we'll try is to make this person really smile, because you know, a smile is always for free, and yeah, has never put any harm to someone, right? Now that we have our handle and target points, it's already time to apply the optimization techniques, the motion supervision and the point tracking from the Drag Your GAN paper. And for this, what we will do is we need our function, a util function that helps us to find the neighbors. This is basically what we saw here. So either we give a distance which will be 3, so we get all surrounding pixels that are below 3, or we can give the 12 for R2, so we get our 11 times 11 patches. So what we could do, for example, is to call the getNeighbors function by calling getNeighbors. The position will be, let's say we put the position 10, 10, which is the X and Y coordinate, and then a distance of 3. So we get our omega 1 for the position 10, 10, basically in our feature maps. And let's see. And here we can see, okay, it's not super easy to read, but we have like all the pixels around. So at the location 8.8, 8.9, 8.10, 8.11. So basically what we saw here, and that would be 10.10, that will be 8.8, for example, and that will be then 12.12. Pretty sure we will find it here, right? Then next we need a util function for the bilinear interpolation to calculate this term, because the direction vector is normalized and doesn't have integer values, so we can't directly access those feature maps or the feature vectors inside the feature maps and have to interpolate them. So what does this exactly mean? This is pretty much a standard way to compute or to write a bilinear interpolation in code. So we have two directions in which we interpolate along the x-axis and the y-axis. So we have 4 different points. This might sound a little bit confusing, but this is basically, you can ask ChatGPT or just look it up. This is how bilinear interpolation is done. And I try to visualize it to make it easier for you to understand. So with regard to this term, this would be, for example, one specific point in our feature map. So we could think this is our QI, and this is our direction vector, which is normalized. So the values in here would range from -1 to +1. And now let's say here's our target. So our direction vector would point from our QI to our target point, which is here. And since the components are still less than 1, our next pixel would be kind of this one, but not exactly. Actually, the value that we would like to access would lay between those two vectors. And what we're doing now, we basically interpolate. We take those 4 neighboring pixels, and depending on how much the digit of the direction vector contributes, one of those pixels will contribute more and one will less. Let's say both components of the direction vector would have 0.9, then this pixel or feature vector would influence our result of the bilinear interpolation way more than this one. But if it would be 0.1, this one would impact our result way more than this one. And with those two helping or util functions, we now can code the main part of the DragGAN paper, which we already discussed in theory. And now first, we will store our initial feature maps after the 6th layer of the initial image, which we use in the point tracking. And also we store the locations of our initial handle points. So we iterate over all handle points and then save their feature vector, so at their initial starting point of the handle points, in our P0 array here. Then we divide the latent that we earlier computed, which is our W intermediate latent, into 3 different parts. So one is the trainable latent, which are the feature maps before and including the 6th layer of this DragGAN generator, and all the feature maps afterwards are untrainable, so they will be frozen during our optimization, which we indicate by requires grad. Then we initialize our optimizer, which will be the ADAM optimizer, using this learning rate, which is also defined in the paper. And here we pass our latent trainable. And what we will then do is, this is basically a helping variable to figure out if we reached all our target points and can stop optimizing. Exactly, so then we break. And what we do here, we concatenate our two latents, the trainable one and the untrainable, to have a combined latent that we can pass to our generator to generate images, because we need all parts. Those are basically the set of styles, so the generator can generate the specific image for us. And it's important to do this within the loop, because this one gets optimized in each iteration. Here we can see we iterate now over our max iterations, and in each iteration our latent trainable gets optimized. So we need to redefine the latent in here. And then we will use the generator, pass our latent and the noise to generate our image and the feature maps after the 6th layer of the DragGAN generator. And we will initialize our loss with 0 in the start. And again, we also have here our variable that we set to true. So basically later we will look, are all our handle points closer than defined by a specific distance, which is 1 in our case, to our target points? And if so, then we can just stop optimizing our image, because our handle points have reached our target points. What we do then is we define our PI and TI, so our handle points and target points. Here we compute the normalized direction vector pointing from our handle points to our target points, so PI to TI. As described, this is just we measure if the distance is closer than our defined value, and then we would break or stop our computation optimization, because our handle points have reached the target points. And what we're doing then is we compute our neighbors, which we saw here. So this is basically our handle point right now, and we have all those neighboring in our basically in our set. And then we iterate over this set. So this would be a QI, this would be a QI. They are all included. So those will be in this green area basically, or feature patch that we saw. So F2 are our feature maps after the 6th layer of the DragGAN 2 generator. And now we use the Y coordinate and the X coordinate of our neighboring pixel. So we can extract the feature vector, which has a dimension of 128. And it's very important to detach this feature vector, because by detaching this one, we make sure that while optimizing using our loss, we optimize our intermediate latent in a way so that our feature, which is at our handle point, moves towards our target point and not from our target point towards our handle point. So this way we don't let the gradient flow through this feature vector here. Then, as earlier described, here we compute the bilinear interpolation by passing our feature maps, and then we add the direction vector with our QI and our feature patch. So basically this would be F1 and this one would be F2. And then we can just use the L1 loss, which we add for each QI. So we have this summation, basically this part here covered in here. And I also did this for the mask, but since I don't have a graphical interface right now, I can't really make a mask. So we can basically skip this part because I won't use it. And then we set all gradients to 0 to prepare basically for a new round of backpropagation and gradient accumulation. And then we backpropagate the loss gradients through our model, and then update our trainable latent by using the optimizer step. So that's basically the motion supervision. Already. So it's actually fairly easy. You can see it's not too much, which I needed to code here. And then as a second step, we will code the point tracking. And for this, we use a proportional grad, because we don't want to update our trainable latent here. We just want to relocate our handle points, because the trainable latent now got updated. So for example, my nose could be right now a little bit like this, and my handle point is wrong. So, we now want to relocate our handle points. And for this, first we again generate our image and the feature maps, and we iterate over all handle points and use those variables to figure out where our closest neighboring feature vector is. So we define again our PI, basically our handle point. We get all neighbors. This time we get more neighbors, so we look within a bigger feature patch, which is of size 23 times 23. And first we here access our initial handle point, which we define in the start, the P0. So that we had defined here of our initial image as well. So where the initial handle point in the initial image was, the Fi we have here. And then we just access our, I've called it F3, which is the neighboring pixel in our omega-2 or in our neighbors, and access there the feature vector. And then we again compute the L1 loss of those two, and then we just compare if our L1 distance smaller than the minimum that we have seen so far, and if so, we assign our minimum new with this L1 distance and also define our minimum X and minimum Y again. And by iterating over all our neighbors, we basically then find our closest neighbor and can then reassign the handle point with this closest neighbor that we have found. And that's basically it. By this we can basically retrack or relocate the handle point in the updated image, and after this a new round in our loop continues. And as I said, this will be continued either until we reach the maximum of iterations which we can state, or if all our handle points are closer to our target points then defined by a specific threshold, which in this case is 1. Yeah, and that's basically it. And what we're doing then, first I convert those to a tensor, the handle points and target points, which I earlier showed already here, those two. Then we will just call our DragGAN method, passing the generator, the latent, noise, our feature maps, the initial ones, and the defined handle points and target points. In each round, we will then take our sample, convert it to an image, so we can later create an animation. We add also our points to that image, so we can see how our handle points get updated and how they slightly move towards our target points. And then at the end, we will just save our edited image as well as an animation video to see our result. Okay, and I think now it's the big moment. It's time to shine, or to see, to fail if this works. So I'll give it a try. All right, and now it's done. We can see it took 4 minutes and 21 seconds to optimize. I'm pretty sure that my code can be optimized, but I thought this would be the easiest understandable way. I hope you agree with me. All right, and now I would say let's have a look at our animations, which we can find in our outputs folder. So here's the image and here's the animated video, and I already downloaded it, so I will show it to you here. So this is how we made our friend smile a little bit more. Yeah, what we can see here, I was hoping I could see a bigger smile. I think I would have needed even 2 more handle points so that his lower lips would stay or remain at the same position, so that it really forces the model to create a smile, because I feel like his whole, if we look at it again, I feel like his whole mouth moves a little bit upper. Well, I was hoping, we could see a bigger smile. But that's one of the limitations that we will anyway see with this paper. So the demos are really, really cool. But as soon as we're out of training distribution, we can quickly reach our limits. The one thing is that we're limited by the DragGAN generator. So the DragGAN generator is just trained on a certain type of, for example, portrait pictures or faces here. So we can't just take any image of us. And another thing is to even generate our intermediate latent or the initial latent for any picture of us, we need something that is called GAN inversion. And let's say like our replicated image with the GAN inversion won't be as precise as our real image. So to use this approach for your own pictures, there are definitely some burdens in between. This is not a replacement of Photoshop, because the GAN inversion itself is not 100% accurate and won't allow you to recreate any image. But for example, if I would take an image of me right now in this position, that could work pretty good. I'm not sure about the background, but at least the foreground, like my face, should be recreatable using the DragGAN model, and then we can basically edit my posture. So you could take a screenshot right now and make me smile, for example. That would work. And I don't want to say that this isn't cool at all. It's super impressive that we can edit images now in such a controllable manner via drag and drop. I just think it's important to also state what this model is not able to do, and the demos are really giving away a feeling that you're like, oh wow, they can do everything, but that's just not the reality. And one more point how I would like to show this is this video where you can see there's like a huge distance for the nose, like a bigger range than for basically to make the person smile. I just had a small distance between handle and target point. And what this will force the model is something it's called basically out of training distribution, because the model doesn't know how it can generate a nose with this face basically being here, like the tip of the nose being here. And what I mean by this, you will see now, because this is a little bit disturbing. So now you can see this starts now getting yeah, out of training distribution, and now the model is basically guessing what it doesn't know. And yeah, here we can now basically see our handle point almost reach our target point. And yeah, this is not the image we were hoping for at all, which looks kind of disturbing. This is a limitation of this approach that I definitely wanted to show you. But as we saw before, it's definitely possible to edit images in a very new and interesting way via drag and drop using this approach. And I just think it's good to be aware of the limitations of the DragGAN paper. All right, and that's it for today's video. I hope you liked it. Let me know in the comments.
Okay, cool. So I thought maybe some of you guys would pause somewhere between the code. I don't know if you guys are just being quiet, but you let him run through all the code. So any questions about the code? Obviously, it's not critical that you understand, but it's often nice to see implementation, you know, and sometimes if you have questions about how things work. So like there was a question about the noise. You could see very clearly in his case, he saved off the noise and used the exact same noise later on. So that's the great thing about code, is it's not very ambiguous, you know.
So also, Ted, it looked like it's not just layer 12 or whatever it is, but all the layers up to there that are allowed to be trained, right?
Yeah, so the interesting thing is the feature map at layer 6 is what does the supervision of the motion, but it is changing the W's for layers 1 through 6.
Right, right.
It's changing all of those. And then you'll see there's two options. In the normal style GAN, when you just run it, there's one W that goes to each of those little A boxes at all the layers.
Mm-hmm.
But for DragGAN, one option you can have is you can allow them to diverge so that each of them is getting a separate update. And so we'll see that in just a moment. That's the difference between what they call W and W+. W+ is they start out the same, but let them diverge.
Right.
And W is keep them the normal style GAN way, where they're forced to be identical.
Right. Yeah, actually, if I recall, in the training for style GAN, that was one of the things they allowed, wasn't it? Where they would split the weights and were expecting it still to generate a good image.
Yeah, in fact, I think they said they thought what you want is you want like that first one just to control hair and that second
Right.
one just to control whatever, right? And so not only did they split it where they had like a first W here at the top and a second W there, they varied where they split them.
Mm-hmm.
And by varying that, they felt that it really forced it to say, oh, because sometimes your W is the same as the 3 layers above you, but not the one below you.
Right.
And sometimes it is the same, then it had to really just force it to say, so you need to do your job. Don't worry about the people above and below. You can't count on them to help you out because they might not have the same W as you.
Right.
Right. At some point, the one above you is going to be different. And at other times, the one below you is going to be different.
Yep.
So you better just focus on doing your job completely and not depending on anybody else. And so they felt that that helped force it to say that the glasses slider isn't going to depend on anything above or below it, that it has to do the full job of glasses all by itself.
Yeah. Okay. And so it sounded like, if I read the code correctly, then the non-trainable layers, those are all being essentially shifted just by a bilinear interpolation. Is that right?
The latents on those don't change at all. So all the finer details stay the same. So for example, what would be what's a reasonable detail? I don't know, like maybe like the curliness of the hair, right? The color of the hair is going to be very early decided, but
Right.
the exact level of curliness might be later than layer 6 or something, right? So what they're saying is that when we're doing motion supervision, we don't want those things to be changing. We want those to be pretty fixed. So that in particular, they want the textures to remain the same everywhere. They're just trying to drag the texture from one pixel location to a new pixel location.
Right. Right.
Yeah.
So
And actually, when I was playing with it, I found that like if I put a handle point in the middle of the forehead, it just basically didn't work because there's not enough texture there.
interesting.
Right? I had to put the handle point someplace that had color, that had hair, that had like variation.
I wonder if that had to do with the point tracking then, because I can imagine the point tracking not working if there isn't sufficient detail.
It was the motion supervision just
Yeah.
initially just flat out didn't work.
Yeah.
And,
yeah.
and we'll see it. We can play with it in just a sec.
Okay.
All right. Awesome. So then, I don't have this in the notes yet. This is the very short, it's only like, what, like 5 or 6 cells that need to be run. This is the Colab notebook I'm going to be showing you. Oh no, I got disconnected. Took too long. All right. Well, it's going to take me a little longer because I have to actually run all these. So what this notebook is doing is it's cloning the official repo from the authors, going to that directory, and it's running a script that the authors provided to copy the pre-trained weights for a handful of different style GANs. So one for lions, cars, faces, elephants. So this is actually one of the slowest steps. It's gonna download like 7 or 8 different pre-trained models that we'll be able to choose from to play with. Once it's done that, there's only Colab comes with most of the packages you need, but there's a couple that aren't. So we're gonna have to install Grad.io and Ninja. Once we have that, then we really have everything we need. All the code is in this repo. So then we can just run this visualizer, DragGAN, Grad.io script, and it'll allow us to create a like a server that I can then open in a new window. So let's just wait for the download to finish, and then we can get things running. So while I'm doing this, if you want, you guys can open the notebook. You can be running it too. Any questions since I need to stall for another minute or two? Help, someone ask a question.
Ted, does this benefit a lot from hardware acceleration?
Yeah, I would assume so. I didn't actually mess around. I just used like default GPU.
Oh, okay.
So I don't know how much difference there is in performance between the T4 A100, V100.
I believe the A100 is considerably more powerful. So interesting.
All right.
Okay.
Well, maybe I should have changed it then, but it actually still runs pretty fast, so that's not really an issue.
Okay.
So
Jeez,
a little bit longer.
How many more pickle files I have? Wow.
Yeah, we don't need all of these, but it comes with some pre-trained models. All right, here we go.
All
So now it's going
right.
to take a little while to install because these are not tiny packages, but we're pretty close.
Okay.
There's Gradio and Ninja. Great. Okay, so now in this box, I'm running the user interface. And so we'll see it's loading the checkpoints, it's initializing some variables, and in a minute, it's gonna actually set up the model.
So this is 512 by 512 image, it looks like.
Yeah, so these are not super high resolution images.
Okay.
This will work. You can use any style GAN. So you can pick a different pre-trained style GAN, but these are the ones that they just happen to have handy.
Cool.
Ted, did you read anything about what inspired them to have this kind of gradual, multiple iteration changing like this?
They do mention in the paper, obviously, like other works, right, and background and stuff. And I think it's the two principles that I talked about, that there is a direct location correspondence between the position in the feature map and the position in the final image. And they use this term. They say that the feature maps are highly discriminative, so that if something looks different in the eventual image, then the feature maps can have different floats also. Okay. So based on those two principles, they said, oh, so then we should basically, like for the point tracking, they actually compared. They said there's other point tracking optical flow things they could use, and they tried them, and they found that actually their simple technique worked even better. Okay. Because they said basically, like, hey, like I said, if this point is a 1, 2, 3, 4, 5, 6, then once it moves over 1 pixel, then that pixel should be a 1, 2, 3, 4, 5, 6. That's just their simple rubric, and it turned out it did work well, and it worked better than using the fancy optical flow stuff. The other one I'm not so sure about, like basically, but the idea that you could basically say, oh, okay, so the features here are 1, 2, 3, 5, 6, 7, 8, and so now let's just get, well, they did it in small chunks, so it's basically 1 pixel over. Let's change that to a 1, 2, 3, 5, 6, 7, 8, and then once you've successfully done that, then let's go another pixel over. And so that whole thing that he showed with like the linear interpolation and stuff, that's because you might be moving on a diagonal. If you were moving directly left, then they would just be trying to move 1 pixel at a time, change the feature map to move 1 at a time. Once you go on a diagonal, then there's that, like interpolation, whatever, kind of business. But if you're just going north, south, east, west, it would literally just be chunk, 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 trying to move it 1 pixel at a time. Now, by the way, just because they're trying to move it 1, because the latent space, we don't fully understand it. It is possible that even though you attempted to move it 1, maybe it actually moved 2, or maybe it moved less than 1.
I assume that's why they had to do add the tracking and the point tracking.
Yeah. And you'll notice the point tracking was 11 pixels in every direction.
Yeah.
Right. If it really worked,
okay.
Yeah, then it should have just been 1 or 2 pixels with all you need to check against.
Okay.
But there's the possibility that somehow by tweaking that latent, it made a much larger jump in pixel space.
Okay. That makes sense. And so that's why, I didn't understand why they had to kind of shift the starting point as they went, but that makes sense what you're saying.
Yeah. All right. So there's a picture that I played with that I found worked. So I'm going to try this guy. All right. So what I'm going to do is I'm going to say add points. And then I'm just going to click once here on this corner of his mouth. And you'll see a red dot. And I'm going to say make a bigger smile, blue dot. Screen's flickering. I wasn't doing that yesterday. I don't know if it's my share screen. And then I'm going to do one on the other. I don't know if I have to, but I'm going to do one here. Big, big smile, mister. And then in the video, he said, oh, maybe I don't want the whole mouth to move. So I'm just going to I'm going to click twice in the same place. And so I'm going to say, don't let the bottom of his lip move. So I don't want his whole mouth to move up like he has a shorter face and a bigger chin. I just want that to stay still. And all right, so then I'm just going to click start. It's got some initialization to do, some loading, and then now it's iterating. So if you see my mouse over here, it shows step 23, 24. It's gradually moving the red towards the blue. As we said, we don't want the blue to move toward the red. We just want the red to move towards the blue.
That's pretty
And
amazing that it knows there's teeth back there.
yeah, so that's the really cool thing is it's not just blurring the existing
Yes.
pixels, it's doing it in latent space. All right, so I could let it, I think the max might be 300, but I can stop it here. I could say I've pretty much gotten what I wanted out of this. Okay. It's not quite stopping. I think sometimes there's a little bit of a delay. All right, so I'm happy with this. I'm gonna say reset. I'm not moving the mouth anymore. I've got a delay. I need to wait for it to catch up. But anyway, so that's the first edit. So like I found that like the whole smile thing is pretty easy. It works quite well. And you can imagine in the training set, this is well within domain, right? You're going to have lots of headshots with people smiling and other headshots. Probably fewer not smiling than smiling. Uh-oh, what's going on here? Worst case, I probably can refresh my browser. What happens?
If it can fail, it will fail when you're doing a demo.
Nice, yeah. Well, at least I got something working before.
No, that did work. Pretty cool.
Yeah, all right. I'm gonna try refreshing my browser. All right, that seemed to be okay. All right, so if I go back to the Flickr faces data set, seed. All right, so I'm not going to do the smile again. Let me show you. I was not able to get him to turn his head. I noticed almost all of these faces are looking directly at the camera. So if I just do a simple thing and I say, here's his nose, turn this way. Click start. And then like, from what I saw, like nothing would happen at all. Just, I'm at iteration 15. And as far as I can tell, there's been no movement whatsoever.
There must be some movement because of the jaggies. Look at the jaggies on the line.
All right, yeah, maybe. But it's not working nearly as well as the smile did. By now that you could already see the smile, right? So then it's like, okay, maybe I need like more texture. So if I click reset points. Uh-oh.
It's going to crash on you again or hang.
It looks like it's hanging every time I stop. So then I tried like, what if I click like here in the mustache area where it's got more texture and it still didn't work. Like I was not able to get, I tried pulling his hairline down, and what I found that my starting point needed to not be, again, just below the hair. It had to be in the hairs where there's more texture. And it was slow. It really had a hard time, but if I waited like 200 iterations or whatever, it could like pull his hairline down, by way of example. Wow. So let me just refresh but let me show you my point. Like, so here's lions, okay? And if I just simply go through, no DragGAN, this is just the vanilla style GAN, just changing the random number seeds. Like, that's kind of a distorted looking lion. The body's like a little, you know, this one, again, the head looks fine by itself, but the body seems a little wrong for it. So my point is, if this particular style GAN is lower res, isn't so great, and has some not so great images, then you wouldn't be surprised if when you start dragging things around, you're really running the risk of running into. See, this one's like just doesn't look square to me. Looks a little smushed.
Like his face goes off a little deformed
Yeah.
to the right there.
Yeah. the
Yeah.
eyes don't match.
Yeah.
Not
This
like
one
that
might have
one.
been in the paper. This one, I think, was the one they opened
Yeah.
the mouth. Whatever. So anyway, so my point was, you know, that, and then let me see if I can see if I can reproduce this. I didn't save a particular one, but
Ah,
I found an elephant, and oh yeah, some of these elephants do not look good. I found an elephant that looked pretty good, and I was like, let me just move the trunk. Okay. So add points. Take the end of the trunk. Hopefully that's a good marker. And I want it to be curled up. All right. So I ran this, it started moving it a little bit, but it was keeping it straight. It wasn't curling it.
hmm.
And then what happened was really kind of funny. It got really confused what to do. And at some point, this became the tail of the elephant, and the head showed up over there. So I don't know if that's going to happen again this time, but I'm going to click start and see what happens. Oh, you see that?
Oh.
That got confused. So anyway, so it's not perfect. I think the better your GAN is, the easier time you'll have. But it's pretty cool, especially if it doesn't hang every time I click stop. But it's not actually stopping, is it?
No, it is. It is.
Yeah.
I don't know what it's doing with that foot.
Oh, this one worked. Yeah. All right.
Could it be kind of like it something wrong with the mask? It kind of like don't know what areas should be included in the changeable tensors.
Yeah. Yeah, we can play with that too. So I can say I only want you to change this part of the image. And then maybe that'll help. But let's see. Okay, so now I need to add my point. So you can see the little highlight, right? This is the masked allowable change region. I'm going to say start here, and let's try and curl it up to here. I think you're right, Shulin. I think this might help keep the head and the tail in the right places, but it's still, for whatever reason, it wanted to keep the trunk straight. It wasn't willing to curl it. And start.
I think it's still trying to tell the elephant.
Now there's a loss if it changes anything outside the mask. It's not absolutely forbidden from changing something outside the mask. There's just a loss to discourage it. So it worked better. But see, it's moving. It's not curling it, but it did move it. So
yeah,
oops.
Nice job,
And
Shulin.
stop. Yeah. So that's the reason for the mask thing, is you get to sort of, that helps. And so again, when you specify a mask, then there's a penalty for any of the pixels outside of the mask changing. So that helps supervise it. So for whatever reason, this elephant model likes really straight trunks, and so I had trouble, getting it to curve. The other thing, if you watched while it was moving, you might have noticed that the red dot might jump around a little bit incorrectly.
Mm-hmm.
Okay, and that's that point tracking is not perfect. And so you can imagine that on the trunk, there are a lot of points that might have very similar pixel values in the eventual image. Not just the point itself, but even its immediate neighborhood. So it wouldn't be surprising if these feature maps had very similar values. And so when it's just doing an L1 loss, it might suddenly say, oh, look, this pixel 6 up and 2 to the right, actually looks closer to the values than that one over there. And so that's
I
why,
think importantly, for the discussion last week, it's not just the L1 loss, but it's the L1 loss at a particular layer. So it's not looking at all of the layers. So
yes.
It's not able to capture, I don't know if the right term is the hierarchy, but the higher level features
Yes.
combined with the lower level features. It's really just the features at that layer. So It's actually kind of, in some ways, kind of guaranteed to be a little bit jumpy on something as monochromatic as a trunk.
Yeah, and that's why I think there really is no way to do this but in small little steps. If you said, let me just try and do it in one big jump move, then you're almost doomed to failure, you know. So, but yeah, and so like I can say, no, I can't. Yeah, I don't know if the UI is going to keep freezing up on me, but once you finish an edit, you can just say like, I'm going to reset the mask, I'm going to reset the points, I'm going to pick new points, and you can do successive edits one after the other. I've been showing you mostly one or two. There's no theoretical limit on the number of handle points and destination points that you can specify. So anybody want to make another suggestion for something else for us to try? We've got dogs,
We
horses.
got cats. What the
Could
heck?
I see the successive changes?
What's that?
Have you done the successive changes, like change and then change and then change and then change?
Yeah. For whatever reason, last night I got it to work. This time, it's like every time I make a change, then my user interface freezes. So I can't really show you the successive changes. But conceptually, there's really no difference, because once you make a set of changes, it's got a W that's coming from. So it's no different than if that was your starting W, right? The model doesn't care. It's just like, okay, I got a W. Now you're going to do some handle points. I'm going to do some things, get a new W. So it's not like you're somehow more distorted of a starting place than the original image, right? They're all just a set of W's. So they're all equal as far as the GAN's concerned.
And they'll all be equally discriminated.
Hopefully.
Well, I mean, it's a woke algorithm.
Right. So like this dog, if we do something simple, can we just
Shut his mouth.
Jerry doesn't like yappy dogs, apparently.
Yes.
Just shut
I'm falling asleep here, so.
what if I just do the bottom? I don't even know.
Okay, well, find out.
So close your mouth, buddy. And I'm not doing a mask yet. We can try that later. Start. So it's initializing the model, and then it'll start doing iterations. Here we go.
It's doing it by
Seems to me-
scaling the head back.
Yeah, it seems to me the head's shrinking a little bit.
He's reverting in age. He's going back to puppy.
Becoming a small-headed dog. All right.
I wonder if
Let's
it
see.
exposes the bias of the training data, right? In some senses, by doing this.
Yep, absolutely. And so
Oh,
there's
yeah.
this business we talked about a little before you joined, Sally. So normally the way the style GAN works is you pick a W, it goes to all of the little A boxes. You have one W that goes to all of these A boxes and all the layers. But one way you can run DragGAN is you can let them diverge from each other, and that makes it a little bit easier for it to generate out of distribution pictures that are less typical of its training set. So let's try.
This is what you kind of hinted at last week.
God, this is just
Looks like you're
not
freezing
happy.
every time.
Yeah, I just keep freezing. So was that dog 0 or dog 1? So that's just the first dog. Okay, so now we can say we don't want the whole head to shrink. So just change this part, please. Oh, I need a bigger circle. I think there's a way to do that.
So
I
brush
thought I
width
saw them
somewhere.
doing it in the demo. I don't know, is this the brush size?
Jack it up and see.
No. It's gonna take me forever.
We can make a new meme called Computer Scientists Drawing.
Actually, if we wanted to torture it, I would like purposefully leave a few parts out of the mask. Like, what? How am I supposed to change this, but not this one little hole in the middle of it?
You need the spray can.
Yeah, but they
It's
did it in the. I saw that in the demo videos on their blog where they changed it to a bigger.
That's a paywall feature. If you pay, you get that one.
Yeah, that's got to be it.
Or it's
All right.
V2, one or the other.
That's as much as I'm doing. All right.
Fair enough.
He's gonna have the most twerked face where like the side of his cheek can move a little bit, but not the whole cheek.
So
Looks like he'll be having an epileptic fit or something.
all right, Mr. Puppy, please close your mouth. There we go.
Go for it. That is interesting. His head is not shrinking. His
Not
ear
shrinking.
placement-
It's still it's tweaking a little bit, but it's trying to, you know, the
Yeah,
mask is helping us. It's
Yeah, it
working.
is definitely. Yeah, it's doing its thing.
By the way, it's running a little slow. It was before. We're still only on iteration 14, and by now we would have been on like iteration 40.
Well,
I don't
maybe
know,
the restricted
server.
mask, you know, it just has to go. Well, you know,
Oh
it's
yeah,
only-
that could be, yeah, the mask might be
Yeah.
slowing it. Otherwise, the server could be just be getting hit a little bit. So I don't know
Well-
if this will look like a perfect dog, but you can see it is now getting the intent, Jerry. It's
This
closing.
does seem like one of those things though, like to complain about it going slowly, right? I mean, if you just kind of look at what you're doing, to use the paintbrush tool on Adobe Photoshop in 1998, just to paint the scene would take longer than this.
Yes. Yeah. But we do have a little bit bigger computer, hopefully, in the back end here on Colab.
Yep.
Are we done? I guess we're done. Oh,
It's still stuck on iteration 22.
well, it was still pretty impressive.
Yeah. All right. So anyway, that's a recap of the paper, the code, not their actual code, but the gist of what the code is, right? You get the 6th layer. In the case of motion supervision, you pick a 5x5 set of feature map pixels. I don't know what the right official name for them is. And again, you move it 1 pixel in the direction that you're trying to get to, the destination, and then you just compute the back propagation. How much should I tweak my W vector to try to get that set of pixels to look more like my original set of pixels? All right. You do apparently just one. I thought they might have done multiple steps, but you just do one step, one tiny little update to W. Then you look at a 23 by 23 patch of so then after you've updated W, you regenerate the new image with the new W. Okay, W prime as it's called. You generate the image with W prime, and you look at the 23 by 23 patch of pixels, and you say, which feature map has the closest values to my original values of the red dot? And if necessary, then you move your red dot a little bit to track the point as it keeps moving. And then each of these steps here is just those 2 steps happening, the pair of steps happening once. And that's a pretty cool way to do like fine control of a GAN image.
Pretty impressive.